All right, guys. So chapter 14, here we go. First lecture video. I'm not going to get into too much detail on the first several slides in chapter 14, but I do expect you guys to read them to get a better understanding. But I will break down a few concepts that you need to know. That being, we are going to talk about forces. So specifically, intermolecular forces and intramolecular forces. This matters because these determine what state a substance will be in. What you need to know is, so we have solids, liquids, and gases. Okay, and according to the kinetic molecular theory, each of these substances are composed of particles, and we learn about this when we study gases. So, but liquids and solids, it's the same thing. We're talking about atoms here. We're talking about particles. So these substances are made of particles. These particles experience attractive forces and repellent forces, or repulsive forces, excuse me, between each other, each particle. These forces determine what state that substance is in. For instance, solid substances, their particles are arranged very rigidly, very compacted. When you look at the pictures in the slides, you'll see the particles are aligned in a neat little square. That's a solid, and the particles are very close together. Those have very strong intermolecular forces. Very strong. Those strong intermolecular forces are because it make it a solid. A liquid, the particles are spread out a little bit more, and the particles have more motion, more movement. They're more fluid. That's a liquid, and the intermolecular forces between the particles aren't as strong. They're medium strength. Gases, the particles are very spread out, and the forces between these particles are very weak, thus making it a gas. This is explained in the chapter, the first several slides in the PowerPoint slides, but I just wanted to make that clear moving forward when I talk about these forces. And intermolecular and intramolecular force is what I'm going to be talking about. Intermolecular force, the prefix inter means between. Between. Okay? Intra prefix means within. Let me break down what the difference is between these. So an intermolecular force is the forces between the molecules, particles, atoms, whatever it is. For instance, here I drew out H2O molecules. So H's and O's, H's and O's, H's and O's. Okay? The forces that take an H2O and another H2O in between those, that's an intermolecular force. It's in between their neighboring molecules, H2O, one molecule, and H2O, another molecule, and there's a force that's bringing those two together. That's an intermolecular force. An intramolecular force, sticking with the same analogy with the H2O, that two hydrogens and an oxygen are bonded together in a polar covalent bond. That polar covalent bond is due to differences in electronegativities, and the hydrogen needs one more electron, oxygen needs two more electrons. They share, that's a covalent bond, and they form H2O. That hydrogen and oxygen, that bond specifically is considered an intramolecular force. Now, there's three different intermolecular forces that I'm going to talk about. However, in this video, I will only be discussing the dipole-dipole force. First, you need to know what a dipole is. Down at the bottom here, explains what a dipole is. So first, let me talk about remember the bonding earlier in the year? I talked about ionic bonds and how NaCl, one was a positive, one was a negative. There was a transference of electron. We did the whole crisscross method. That's ionic bonding. Covalent bonds, they share electrons. So if hydrogen has one electron in its outermost shell, it needs two to satisfy the orbital. So let's say this example right here. So HCl, okay, hydrochloric acid, HCl. Chlorine has 7 electrons in its outer shell. It just needs one, because remember the octet rule. 8 electrons fill that outermost shell. It just needs one. Hydrogen needs one. They come together and they're satisfied. Boom. They're satisfied. Hydrogen picks up one and it's good. It's got 2 now. Chlorine gets 1 from hydrogen. It's good now. It has 8. And it satisfies that octet rule. If you remember the whole dot diagram, Lewis dot diagrams, if you remember that at all. Now, this is a covalent bond. But there's 2 different types of covalent bonds. It's nonpolar covalent bonds and polar covalent bonds. Let me write that. So you have polar and nonpolar. Polar covalent bonds means so let's look at this example. If it's polar, that means that there's a difference in a great difference, between the electronegativities of each atom. Chlorine is all the way in the 17th column, but 7th in the P, all the way to the 17th column on the periodic table. So all the way to the right. Hydrogen is all the way on the left in the first column. That gap between the periodic tables shows a very big difference in the electronegativity values. Chlorine really high, hydrogen really low. Because there's such a huge gap between on the periodic table between the electronegativity values, it's considered polar. Large difference in the electronegativity values. Okay? Now, nonpolar just means they have similar electronegativity values. They're similar. So this whole shape here doesn't happen in a nonpolar covalent bond. Now let me focus on the polar and this shape. Think of an electron cloud. Electrons circle the nucleus of an atom and they gravitate around. Well, this cloud shape takes form in polar covalent bonds. H2Os, HCl's are all polar covalent. And this shape is always a result. This shape right here is a dipole. This is considered a dipole. Remember, hydrogen has 2 electrons floating around it. Chlorine now has 8 electrons floating around it. But because chlorine has such a greater electronegativity value, that means it's stronger. It has a stronger attraction for electrons. Think of tug of war. Chlorine's got hydrogen beat tenfold. And so therefore, if hydrogen and chlorine get into a tug of war match, it pulls on that rope way harder and pulls hydrogen in really close to it and beats it. With this analogy, chlorine is so strong that all the electrons gravitate away from the hydrogen. The electrons gravitate away from the hydrogen and gravitate toward the chlorine. So you have a bunch of chlorines hanging out around, or a bunch of electrons hanging around the chlorine, and very little electrons hanging around the hydrogen because chlorine's stronger, has a higher electronegativity. This is polar. So, electrons are gravitating around here, around the chlorine, away from the hydrogen. It forms a dipole. Okay? Because of this accumulation of electrons toward the chlorine end and away from the hydrogen end, chlorine picks up a partially negative charge. And hydrogen, because all the electrons are leaving the hydrogen and going towards the chlorine, even though they're bonded together, most of them are gravitating towards the chlorine, it picks up a partially positive charge. And if you remember, Opposites attract, similar charges repel. That's important when we start talking about the dipole-dipole force. So chlorine picks up a partial negative, hydrogen picks up a partial positive charge because electrons are going away from the hydrogen towards the chlorine. Remember, electrons are negative. A surplus of negative electrons are now hanging around the chlorine, thus resulting in a partial negative charge. Dipole. Now, the first out of the three intermolecular forces that I'm going to be discussing is the dipole-dipole. Dipole-dipole. H2O is another polar covalent bond. Remember, if it's polar, that means a dipole is occurring. A dipole is occurring if it's polar because of the great difference in electronegativity values. Nonpolar, similar electronegativity values. This doesn't happen. There are no partial anything going on. And I'll talk about dispersion forces either 2 days from now or tomorrow. We'll see. So, H2O, polar covalent bond. Oxygen and hydrogen. Hydrogen, low electronegativity value. Oxygen, high. It's in the 16th column. It's in the 16th column on the periodic table. Big gap. That means a large difference in electronegativity values, which means it's polar. Oxygen's way stronger than hydrogen. Therefore, electrons around the hydrogen gravitate towards the oxygen. It gravitates towards the oxygen because oxygen has a stronger pull on those electrons. So all the electrons are now gravitating towards the electrons and away from the hydrogens. Oxygen acquires, because of this accumulation of negative electrons, it acquires a negative, partially negative charge. And each end of the hydrogens acquire a partially positive charge. It's just partial. Why? Because electrons are leaving away, the negative electrons are leaving away from the hydrogen, positive, it's acquiring positive, and going towards the oxygen. Surplus of electrons towards the oxygen makes it partially negative. So therefore, H2O is a dipole, has a dipole. Hydrogen or H2O is never by itself. If you have a pool of water, there's billions of H2 molecules all throughout it. And there are dipole-dipole forces holding each H2O molecule together. At random times they break, come back together, break, come back together. A simulation on this chapter will demonstrate this. You should check it out. Anytime a partially positive hydrogen comes in contact with a partially negatively charged oxygen in the H2Os, they bond. So this hydrogen is now bonding with oxygen. Remember, positive and negatives attract each other. So this forms a bond between the two H2O molecules. So you can have thousands of H2O molecules bonded together because of the intermolecular force of the dipole-dipole interaction. So this partially positive hydrogen will get close to the partially negative oxygen, and they'll attract each other and form an intermolecular bond due to an intermolecular force called a dipole-dipole. I hope that makes sense to you guys. I will definitely break this down further for you guys if you need me to. Just pause, rewind as you need, and I'm going to be discussing the 3 intermolecular forces. Y'all have a good one. See ya.